honored today to share our research on improving GPU sharing performance through adaptive Bubbleless spatial-temporal sharing. And my name is Shulai Zhang, and I'm from Shanghai Jiao Tong University. So first, let's address the question, why do we need GPU sharing? And there is a clear trend that the computational power of a single GPU is increasing dramatically. And take NVIDIA's data center GPUs as an example, with the evolution of architectures from Volta to Ampere and now Hopper and the upcoming Blackwell, a single GPU can deliver significantly more compute resources than ever before. While people are leveraging these powerful GPUs for large language models and other intensive workloads, there are still many lightweight applications that don't require the full capacity of a single GPU. For instance, some applications may not utilize all the streaming multiprocessors on a GPU, or their quality of service requirements are lenient, meaning they don't need substantial resources to complete their computations. And given this context, GPU sharing emerges as an excellent paradigm for lightweight workloads to efficiently utilize a single GPU. And now let's dive into the workflow of how multiple users share a GPU. When users or applications need to access the GPU, they first request the specific quotas based on their computational requirements. And the cloud vendor or GPU provider then allocates the necessary computational resources to these users with the performance guarantee. And the key challenge here is how to achieve this effectively, how to schedule and manage on-chip resources to deliver the promised performance guarantee. And the entire workflow of our GPU sharing system is divided into two main parts. First, at the deployment stage, applications register with the sharing system and establish their own contacts and allocate device memory on the GPU. And this is essentially the offline preparation phase. And then at runtime, when co-located applications need to use the GPU, they submit requests and launch their kernels to the GPU. And by default, the hardware scheduler fetches these launched kernels from the device queues and dispatches them onto the streaming multiprocessors. However, once the kernels are launched onto the GPU, we lose direct control over them or over their execution, as their behavior is entirely managed by the hardware scheduler. To ensure the performance guarantees for shared applications, we introduce a custom scheduler at the host level. And this scheduler ensures that real-time execution and GPU resources remain under our control. And this is the core logic of our GPU sharing system. And now let's review the basic patterns of how resources are shared across applications on a GPU. Let's see an example, like a request from a VGG model application arrives first, followed by a ResNet request that wants to share the GPU. And temporal sharing treats GPU's time slices as the primary resource, where users take turns using the GPU in a round-robin fashion. And on the other hand, spatial sharing treats streaming multiprocessors resources as the primary resource, allocating them to different applications. And however, both approaches have significant limitations. They fail to provide efficient resource guarantees and often introduce bubbles during GPU execution, leading to low utilization and suboptimal performance. And with an ideal sharing scenario would be this. An application can fully utilize the GPU without restrictions when no other applications are running. And when co-location is required, smart sharing strategies are employed to ensure all applications perform well. And this eliminates resource bubbles and prevents performance degradation caused by interference, resulting in optimal utilization and performance for co-located applications. And existing GPU sharing solutions suffer from several inefficiencies. And first, resource bubbles is the significant issue, particularly in static sharing methods like static temporal sharing and static spatial sharing. Fixed resource management often leads to many unexploited bubbles. And second, unbounded sharing solutions such as those using CUDA multi-streams or multi-process service like MPS. Those methods introduce kernel execution interference, and in these cases, the latency of each request is suboptimal. For instance, although the kernels of the first client request are launched first, the arrival of the second client's request can interfere with the execution of the first client. Due to the uncontrolled and interfered kernel execution sequence, the latency of both requests becomes suboptimal. And third, biased sharing methods prioritize the collocation of real-time tasks and best effort tasks. While these methods ensure the performance of high priority tasks through techniques like kernel fusion and preemption, they often leave bubbles unutilized. And an ideal, fair, and unbiased GPU sharing system could be implemented as shown in this figure. And first, to centrally manage kernels from different applications on the host side and reduce the overhead of intercepting and scheduling each kernel launch is necessary to determine an appropriate scheduling granularity. For example, the scheduling could manage multiple kernels at once, as depicted in this figure, where kernels are grouped and scheduled in squads. And second, to achieve better resource utilization efficiency, the sharing system must support precise resource control and real-time management during runtime. And third, in addition to resource control capabilities, fine-grained sharing also requires the ability to rapidly reconfigure resources. And once these requirements are met, we can re-examine the request latency under different sharing mechanisms. In an ideal and biased scenario, the shared execution of VGG and ResNet achieves the lowest latency. To achieve this highly efficient sharing effect, our work designs a system divided into two phases. And the first, the offline deployment phase, where the sharing system uses offline performance analysis tools to analyze user applications and stores the results in a database. And second, the online execution phase, which includes three components to ensure efficient scheduling and execution of shared applications. And the first, the multitask scheduler, and second, the execution configuration determiner, and third, the concurrent kernel manager. So to ensure the performance of co-located applications, we employ a multitask scheduler to organize and schedule kernels in groups, which we refer to as kernel squads. And specifically, to form a kernel squad, we track the progress of each request and carefully select kernels step by step to meet the isolated latency targets of all co-located applications. We continuously monitor both the real-time progress and the expected progress of each co-located request. The core idea of our scheduling algorithm is straightforward. That is, prioritize scheduling kernels from requests that are lagging behind in progress compared to others. By doing so, we ensure unbiased sharing by evenly distributing the execution progress across all concurrent requests. And after determining the scheduling method for kernel squads, the next step is to identify a good execution configuration for these squads and manage the resource correspondingly. This is achieved through the execution configuration determiner, whose goal is to minimize the execution time of each kernel squad. And the key lies in effectively modeling the runtime behavior and performance of kernel squads while also estimating their execution conditions during runtime. And we categorize the execution behavior within kernel squads into two types, each predicted using a different predictor. And first, bounded sharing, where there are no restrictions on resource usage among kernels within the squad. For example, in this case, kernels from NASnet and BERT freely compete for resources. However, since BERT's kernels have longer execution times, the NASnet kernels complete their execution earlier in the squad, leaving the remaining BERT kernels unable to fully utilize the hardware resources. This inefficient overlap leads to resource waste, causing the kernel squad's execution to exceed expectations. Second, the spatial sharing, where resources are strictly partitioned within the kernel squad. Due to these rigid resource constraints, when kernels from multiple applications cannot finish simultaneously, some kernels end up using only a portion of the resources they could otherwise fully utilize. This also introduces resource fragmentation. To determine during runtime whether a kernel squad without resource restrictions or one with restrictions has a shorter execution time, we continuously run two latency predictors on the host side. And for the unrestricted kernel squad latency prediction, we use a workload equivalence predictor. And for the resource restricted kernel squad latency prediction, we use another interference-free predictor. And more details are in the paper. And next, we developed a concurrent kernel manager to manage resources for kernel squads in practice. First, we pre-establish multiple MPS contacts, each with different compute resource configurations. And this allows us to enforce compute resource restrictions for individual kernels. And second, these MPS contacts are actively maintained during runtime, enabling rapid resource reconfiguration as needed. So as we stated earlier, we observe a tail effect in the execution of kernel squads, whether under unbounded sharing or spatial sharing. So to address this, we employ spatial-temporal sharing or semi-spatial sharing to further mitigate the tail effect and reduce the overall duration of kernel squads. And as shown in this figure, kernels at the beginning of the squads are subject to SM restrictions, while the restrictions are lifted in the later stages, allowing all kernels to fully utilize all SMs. So to achieve this, kernels within a squad are launched into different MPS contexts in real time, and each user application has a primary context with no resource restrictions and multiple MPS contexts with varying compute restrictions. So now that we've constructed an efficient GPU sharing system, let's move on to the evaluation section. And for the experimental setup, we use an NVIDIA A100 GPU as the base hardware. We evaluate both inference and training benchmarks, deploying models such as NASnet transformer-based models like BERT and others. And we've manually constructed workloads with high, medium, and low intensity levels and tested them on real-world traces. And as for baselines, we compare our system with several SOTA GPU sharing mechanisms to demonstrate its effectiveness. And compared with state-of-the-art GPU sharing system, the average latency deviation for co-located application is no larger than 1 millisecond when measured against the isolated latency target. And this offset represents only 3% of the request's end-to-end latency, and demonstrating the precision and efficiency of our system. And for the average latency of co-located inference applications is reduced by up to 37%, thanks to our system's ability to eliminate GPU bubbles and schedule kernels in a more efficient manner. And the latency reduction is not that prominent in training scenarios because the training workloads are typically heavier. However, thanks to Blast's more efficient resource management and its ability to organize highly optimized kernel squads, we still achieve an average 14% reduction in duration per training epoch. And BLAS demonstrates excellent scalability, performing well in scenarios with uneven quotas and when more than 2 applications are collocated. For example, it handles cases with 4 or even 8 collocated applications effectively. Additionally, BLAS can guarantee the quality of service for applications without disrupting internal mechanisms simply by adjusting parameters in the scheduling algorithm. And so here's the conclusion. And BLAS is a multi-user GPU system to deploy multiple applications on a single GPU. And it utilizes the unused bubbles of a GPU to provide the promised latency for applications with specific quota provision. And it schedules kernels in units of fine-grained kernel squads and then enables precise resource management. And so BLAS reduced the average latency for collocated applications compared to SOTA systems. And that's all. Thank you.